So this is not my first talk at the PyTorch meetup. I had another one half a year ago, and I thought this one is going to be the opposite. Last time, I talked about the guts of implementing machine learning stuff. So I talked about the assembly instructions that go into the CPU and GPU kernels for matrix multiplications and linear algebra, all of the attention mechanism that then would go into PyTorch, and afterwards empower the PyTorch users. This time, I'm only talking about high-level stuff. So we're taking a tool, and we're going to be using it without knowing how it works under the hood. Secondly, last time I talked about optimizing compute. But assuming we all work on John von Neumann's architecture of a computer, compute is not the only part. Aside from logic, there's also memory. And where we optimize assembly instructions, we should also think about optimizing I/O, input-output operations. So this time, I'm talking about optimizing I/O, input and output. Last but not the least, last time I was talking about assembly instructions and praising the chip makers, whom I adore. This time, it's going to be shameless self-promotion. Last time, the content of my talk ended up going to a repository called CVP, which ended up on Hacker News main page afterwards, which was like a lucky strike. This time, I'm talking about a repository that's been used for a much longer time. It's called usearch. And the reason it's relevant is because it's arguably one of the three world's most widely used search engines. So there are three that I generally compare. One of them is Apache Lucene. The second one is Metaspace, and the third one is the one that I wrote and published a couple of years ago called Unum's usearch. Arguably, it's like the newest one, maybe the most minimalistic, but also potentially not most widely used in terms of the number of operations per second, search queries per second handled around the globe. So the first one, Apache Lucene, is under the hood of Elastic. So if you use Elasticsearch, you're using Lucene. If you're using Solr, you're using Lucene. If you're using Cassandra, MongoDB Atlas, which is actually quite surprising, because MongoDB is mainly written in C++, but MongoDB Atlas is mainly written on top of JVM. So they chose Lucene for the search engine part, and Azure Cognitive Search, of course, as well, is Lucene. The other one that probably has the widest adoption within the Python ecosystem is Metaspace. It's under the hood of Milvus, Vault, V8, Pinecone, and Tootrand. All of those are with stars. So by that I mean that I'm not entirely sure if those companies still use it. Many of them have claimed that they've moved on to custom implementations of HNSW, which is the hierarchical navigable small world graph algorithm that powers most of vector search around the globe. Last but not the least is the search engine that I wrote. It's under the hood of ClickHouse, DuckDB, Yugabyte, ScyllaDB, TiDB, MemGraph, and Vault again. So some of the databases support multiple backends. And those are just the open source companies. Most of the others include closed source as well. If we include closed source, it would also include most of the largest AI labs and a lot of the intelligence and government organizations around the globe. So why do people choose any one of those? Of course, they have different benefits. For Lucene, I think practically the only one is it's a JVM native project, and it's very, 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 very old. It's 27 years old now. So it was published in 1999. And because a lot of the distributed computing software has been written in Java, the ease of integration with a Java native toolkit for search has been a predominant factor for Lucene's adoption. The second one, Metaspace, like most of the infrastructure software written by Meta and Google over the last 20 years or 15 years, is C++. In many ways, it's the most versatile toolkit of the three presented here. So you can choose what kind of algorithm you want to run under the hood, what kind of indexing data structure. But the most adequate real data structure in use today would be still HNSW, which is also implemented by usearch. So when I was writing the search engine, my logic was the following. How do I implement the search engine that has expectedly high performance on large devices, like super powerful servers, and can power significant databases, but is also portable enough so that people can run it anywhere, even on embedded devices? So it involves a lot of very low-level tricks, because I write a lot of assembly for x86, ARM, and NVIDIA chips. And right out of the way, I wrote the first version over the 4 days, or like a weekend, and it had 4 bindings for 4 different programming languages, C, C++, Python, and Rust. But over time, the first-party support, meaning that the language bindings that exist within the same repository, grew to 11 programming languages, including also Swift and Java and even obscure programming languages like Wolfram that are used in very rare environments. And then there are programming languages for which the community has created third-party bindings, which is very nice. But the reason it's like so freaking powerful is because of those SIMD instructions. So my entire previous talk was about how compilers cannot generate some of those interesting instructions that form the majority of the vocabulary of modern CPUs. And for this library under the hood, I wrote another library called SimSimd, which packs not one, not two, but of the order of 500 handwritten SIMD assembly kernels at this point, covering the widest range of CPU architectures and metric functions you can find on GitHub. So it's a really obscure source of wizardry on how to make CPUs do weird stuff. For example, last year we found a way to squeeze 330 gigabytes per second worth of throughput in accumulating numbers on a single AMD CPU core, just scanning through CPU registers and level 1 caches. And last but not the least, you'd think, okay, 500 assembly kernels is too hard, but from what I hear, it might be the easiest of the three to use. I'm super biased though, so like, this is gonna be my Achilles heel of this talk. I'm super biased. Get ready to roast me afterwards. Luckily for me, not all of my praises come just from myself. So there has been, surprisingly for me, research labs that actually wrote papers about some of the search engines. I never have time to write papers, to be honest. Like, I maintain about a dozen major open source projects for the last few years, and even today, this is the first time I'm seeing this presentation, because I was just like preparing the slides while others were talking, and surprisingly found a JVM bug, I guess. So started looking into OpenJTK as well. But anyways, there is this cool research lab very close to here in Europe, just an hour flight from here, that took Face, which is actually a lot faster than we've seen, and compared to USearch, still claiming 10 to 30x performance improvement on a very small data set. Well, I was mainly optimizing for very large ones. So when I run my own benchmarks on very large data sets, like hundreds of millions of vectors, I generally notice that there's certain kinds of data structures that are really weirdly designed within Meta's search engine, so that they spill outside of the CPU caches, causing one more lookup in random access memory, and then refueling the caches over and over again, kind of repeating the spills. So after about 40 million entries within Face's proximity graph construction algorithm, there is a significant bottleneck that is faced, and after that there is about 200x performance difference at the construction. So it was like not very easy to benchmark this, just because your benchmark completes within like a few minutes, and then to measure up the competitor, you spin up a machine with several hundred cores, and you wait for days. Actually, for this talk, I have a 192 core AWS machine running right now, but there is no way it's going to complete the Lucene benchmark before we finish the talk, sadly. Forget Face, forget Meta, we're talking about Lucene and the JVM ecosystem and scaling with Spark here. Scaling out is a bit weird. First of all, I absolutely hate scaling out. You should never do it. Realistically, if we look at the absolute majority of teams and companies around the globe, it's very hard for me to imagine the scale at which one single server cannot process your workload. So absolute majority of companies will never face that scale. Realistically, a modern computer, even without GPUs, can squeeze of the order of 200 gigabytes per second worth of memory throughput. It's just that most of our software is not really designed to like handle parallelism at this scale, and also the memory throughput on the non-uniform memory architecture systems. So hence, most of us who don't want to waste too much precious time, developer time, decide to scale out because it's easier but more expensive in terms of compute time. So when you use Spark, first thing to notice is that it has like a convenient way for you to deploy kind of a semi or pseudo-distributed set of programs, so that if you want to just like perform some raw benchmarks and see if your system is ready for distributed execution, you can just like slice your current node into multiple parts and make sure everything works fine. That's what I was doing here. And when we do horizontal scaling of like vector search or any kind of search workloads, the construction phase is pretty simple. Just depending on the key of the entry, we can hash it and decide on which machine we want to put the entry. But it's important to remember that the search phase will suffer. During the search phase, unless you have some smart algorithm on how you shard information, you're going to be all scattering the queries and all gathering the results. and post-filtering them afterwards. So keep it in mind that in this case, you have this form of search amplification if you start in a naive fashion. Designing a non-naive fashion is like highly non-trivial, so most people never do it. There were a million things I tried to do with Lucene, and frankly, I'm the worst person to do that. Every time I touch a JVM-based system, I suffer. That's been the story with Neo4j for about a decade for me now. Like, I never managed to run that thing on a graph with over 100 nodes, and my average default startup point is 100 million, not 100. So with Lucene, I suffered all over the last week. And then I reached out to a bunch of people who work for Apache Foundation to ask them, what the hell am I doing wrong? So we worked back and forth with a few of them, and it seems like I did what I could. So important tuning points for Lucene, if you deploy it, is to realize what kind of key lookups are you going to perform. Are you going to retrieve the vectors afterwards or no? Do you need to convert them into the internal address space of the Lucene index? Another big question is like how those JVM-based systems perform parallelism. Most of them cannot really do concurrent data structures, so they split an index into multiple different segments, and then at best, they will allocate a few segments per thread. But that's actually pretty bad from search perspective because, as we know in computer science, building up searching data structures, you want to make the data structure as big as possible because your asymptotic complexity of most search operations is a logarithm of the overall size. And if the size is getting bigger, then you're kind of reducing the depth of your search by leveraging this like log property of the data structure. Then there is the pitfall of almost all data processing systems, especially the ones that are designed for persistent memory, which Lucene originally is. So not everyone runs Lucene in memory. Most people probably run it on disk, which I didn't. I overwrote the mechanism in which Lucene is preserving information so that it would keep everything in memory. But because JVM is old, it has a hard time with 4 GB and large buffers, so I had to write custom buffers and custom sharding, a lot of boilerplate. And all of it was horrifying, but I have to be honest here, USearch wasn't perfect either. So I've never actually used myself, my own search engine in a proper job environment. I only know a couple of like big Solr and Elastic users that switched to USearch, and they told me over time that the transition period wasn't perfect, and I didn't understand why. Now I realize. So in preparation to this talk, I actually went back and forth and designed a mechanism to package what I call fat jars, or like not just me, everyone calls them fat jars. It's just like a common term. A jar is like this package of Java modules, I guess native to half of the people here. But a fat jar would be a package that contains a lot of different precompiled distributions for different CPU architectures and operating systems with different linking mechanisms depending on the OS. So this way, if there's one big fat jar, inside of that jar, you have a sub-jar for Linux, Mac OS, Android, and Linux, as well as 64-bit ARM, 32-bit ARM, x86, and a few different variations that are precompiled ahead of time, and MyCI always publishes it so that in your build mechanism, you need to pull it. So this is the weirdly hardest part of using USearch, just making sure that your Gradle pipeline, which is like Spark related, pulls it and then passes to the JVM the right path to native library. All of this suffering, this whole nightmare of dealing with Lucene for a few days, instead of maintaining actually complicated assembly code, resulted in this poor benchmark, which is public on my GitHub profile. So USearch natively supports a lot of data types, including brainflow 16 and flow 16 that are not supported by JVM. So I kind of kept this for comparison, but under the hood, USearch would convert to BF16 or F16 depending on the use setup. I tried everything I could to balance out the construction speed versus search speed. It took me several days, and I pulled a lot of people, and I couldn't make this significantly faster. Maybe at best I would squeeze the QPS, which is queries per second, search queries per second, so let's say 10, 20,000, but the construction speed would suffer then. Or on the opposite end of the spectrum, the recall on the normalized discounted cumulative gains, which is the default measure for search quality, would suffer. So when you benchmark search, this is the holy trio. Construction cost, search cost, versus search quality. Construction cost is insertions per second for any vector search engine. QPS is how fast you can search. And for quality of search, it's either recall, which is a simpler metric, or normalized discounted cumulative gains. So I make sure gains, like the recall, both are comparable. And then I couldn't get to a point where the difference between the search engines will at least be within the order of 10x. Even that was hard, even on a scale of just 100 million vectors, not even a billion. But for this thing, I sometimes benchmark it of the order of 30 billion vectors per single node. And I thought, would it get better if I use Spark? I'm not sure, to be honest. I wrote a ton of scripts, and I'm running the benchmarks now as well. It seems like I found some JVM bug, but I'm not sure. But during this testing period, I've uncovered a few interesting aspects. The first one was that my assumption that JVM being not great at handling 190 core machines and would get better if I slice it into smaller parts would somehow magically make Lucene run. That didn't happen. The other few aspects is that you have to be very careful, not just with tuning to the JVM and the Lucene index, but also tuning Spark. So you need like about 100 different tumblers that you pull back and forth to see how well it works. With research, it's only like 2 hyperparameters, and those are optional. To get back to this is the list of aspects that there are, and at the JVM part in the bottom of this page, it's actually a summary of things I tried. First, you need to enable SIMD. So the things I write by hand, there is an assumption within a lot of high-level programming language communities that compilers can generate those, including Java's runtime, which is not feasible, to be honest. Like they tell you to enable this, it will never help you to beat handwritten assembly. Another aspect is that you must enable transparent huge pages if you're working on the machines this size. It also never helped. I tried every single configuration to tune the garbage collection system, as well as to disable garbage collection entirely, because I'm running on a machine with 1 terabyte of RAM, and I'm only dealing with a dataset that is only 10 gigabytes, but even that didn't help me. So it's been a nightmare of a few days just to get to this slide, same or worse. And the few other things that I noticed is like within this ecosystem, it's very important for you to disable call-less sharding so that your shards don't get up on the same subnodes of Spark. It's very important to configure JVM in such a way that for every sub-Spark, it creates a sub-JVM and they don't share the same address space, because otherwise they will be competing for resources. And actually, the Achilles heel of USearch ended up being propagating native library paths. So that was tricky. Making sure that not only the main JVM runtime recognizes where all the precompiled libraries are, but also passes it down. So this gave me a lot of food for thought on what I'll be working next and how I'll make the transition for the Spark ecosystem much easier. But hopefully you can also get something out of this talk and make sure that you combine your native code, like PyTorch, with JVM ecosystem projects in much nicer fashion. With this, I'm going to conclude. If you're interested in this kind of systems engineering, I maintain a ton of libraries, including one of the world's most widely used search engine, fastest string implementation, I guess, ever published, a prototype of the RPC library about 70 times faster than Fast API, a lot of mixed precision numerics, and other tricks, including very parameter efficient and data efficient pre-trained models, sometimes on top of PyTorch, sometimes on JUX. That's it. Thank you very much. I'm open to questions.